Hello everyone, I am Bu Ling, which is a student from the Mathematics Department of Xiamen University Malaysia. Today I'm going to have a presentation about the proof of the open set definitions of continuous function as well as its applications. So let us look into the theorem. So this is the theorem of the open set definitions of continuous function. Let U be an open subset of Rn and consider the mapping of the function f from U to Rn. Then the following two assertions are equivalent. The mapping of the function f from U to Rn is continuous if and only if whenever V is an open subset of Rn, the preimage f inverse of V is an open subset of Rn. So now I'm going to prove for this theorem. Assume that the function f is continuous on U and that V contained in Rm is open. Let A be a point in f inverse V, then we have f of A contained in the open subset V. Since V is an open subset, there must exist an open ball with positive number epsilon such that the ball with radius epsilon centered at f of A contained in the open subset B. Since the function f is continuous at the point A, by the epsilon delta definition for continuity, there must exist a positive number delta such that the norm between f of x and the f of A is less than epsilon whenever the vector x contained in U and the norm between x and A is less than delta. So we have the x contained in the ball with radius delta centered at A, and this implies that the function of x, the function f of x, is contained in the ball with radius epsilon centered at f of A. In particular, we have f of the ball with radius delta centered at A is contained in the ball with radius epsilon centered at f of A, which is also contained in the open subset B. Thus, we have the ball with radius delta centered at A is contained in the f inverse of V. Hence, we prove that the f inverse of V is open. Firstly, suppose that f inverse of V is open whenever the V is contained in Rm is open. Then we want to prove that the function f is continuous at each point in the open subset U. Let A be a point in U and epsilon be a positive number. Then the ball with radius epsilon centered at f of A is open in Rm. Since the ball with radius epsilon centered at f of A is open, the preimage f inverse of the ball with radius epsilon centered at f of A is also open. And since the point A is contained in the f inverse of the ball with radius epsilon centered at f of A, there must exist a positive number delta such that the ball with radius delta centered at A is contained in the f inverse of the ball with radius epsilon centered at f of A. Then we have the f of the ball with radius delta centered at A is contained in the ball with radius epsilon centered at f of A, which is also contained in the open subset B. This means that the norm between f of x and f of a is less than epsilon whenever the vector x contained in U and the norm of x, norm between the x and a is less than delta. Next, we prove that the function f is continuous at the point A. And since this is true for all the points of A contained in the open subset U, we conclude that the function f is continuous on U. So now we are going to look into the applications of this theorem. Question 1. Suppose that the functions of f from Rn to R and the function of g from Rn to R are both continuous. Prove that the set of the point U contained in Rn so that f of U equals to g of U equals to 0 is closed in Rn. So this is the solutions provided. Let U be the union of the open interval of negative infinity to 0 and the open interval of 0 to positive infinity. Since U is the union of two open sets, then we know that it is open. And since the function f and the function g is continuous, we know that the f inverse of U and G inverse of U are open sets in Rn. C1 is a set of the points U contained in the Rn so that f of U is equal to 0, and C2 be the set of points U contained in Rn so that the G of U is equal to 0. And since C1 is the complement of the f inverse of U in Rn, it must be a closed set. And similarly, C2, which is the complement of G inverse of U in Rn, it is also a closed set. The set for the points U contained in Rn so that f of U equals to G of U equals to 0 is equals to the intersections of the set C1 and C2. And we know that the intersection of C1 and C2 is closed since the intersections of finite closed set is closed. Hence, we have proved that the set of the points U contained in Rn so that f of U equals to G of U equals to 0 is closed in Rn. Next, move on to the question 2. Let f from x to y be a function. Prove that the function f is continuous if and only if for every closed subset D inside the Y, the inverse image f inverse D is closed in X. So this is the solutions for the question 2. Suppose if f is a continuous function, let D be a closed subset in Y. Then the complement of D in Y is open. And from the theorem, we know that f inverse of the complement of D in Y is also open. Then we have the f inverse of the complement of D in Y equals to the complement of f inverse of D in X, which is also open. Hence, we prove that the f inverse of D is closed. Conversely, assume that f inverse of D is closed for every closed subset D in Y. We let U be any open set in Y. Then the complement of U in Y is closed. Then we have the F inverse of the complement of U in Y equals to the complement of F inverse of U in X, which is closed. And since the F inverse of U is a complement of a closed subset, it must be open. And since the pre-match of any open subset U is open, we have proved that the F is continuous by the theorem of open set definitions of continuous functions. So that's all for my presentation. And I hope that everyone of you will have a better understanding of the open set definitions of continuous functions.